This video will demonstrate how to set up a Polyflow blow molding simulation using a shell mesh. The end results of such a simulation are shown in this animation. As you can see, the shell mesh will start off as a cylindrical parison and will then be pinched off by a moving mold and inflated so that it takes the shape of a bottle that could be used to package, say, liquid soap. To begin, I'll create a Polyflow analysis system in Workbench and use the right mouse button to open the menu that allows me to read in the mesh file. Next, I'll double-click the setup cell to launch PolyData, which I'll use to set up the simulation. As you can see, when creating the meshes, I took advantage of the symmetry and only modeled half of the problem. I have separate shell meshes for the mold and for the parison. The axis of the parison is oriented in the Y direction, and the mold will approach the parison along the Z direction. By clicking the Mesh tab, I can view information about the mesh. I can see that the mesh subdomains are appropriately named mold and parison. The Info button allows me to confirm that the units used to create the mesh was millimeters, which is consistent with the overall dimensions shown here. Since PolyData doesn't manage units, it's my responsibility to consistently use millimeters as the unit of length for all of the settings that I will specify. Back in the Menus tab, I'll create a new task for this simulation by clicking the appropriate menu item. This opens a deeper level menu where the selected attributes of the task are noted by arrows. I'll retain the default selection that defines it as an FEM task and indicate that it's a time-dependent problem that involves a 2D shell geometry. Accepting the setup will open the task menu. Here, I'll begin by defining the mold. I'll create a new mold and specify that it's adiabatic, accept the default name, and then define the domain to only include the mold mesh, so I'll remove the parison mesh. Clicking upper level menu will return me to the previous menu. Now in the steps that follow, I want some of the settings to be time-dependent, so I'll click the Eval button. While this button is enabled, I will be prompted with menus that allow me to define the time dependencies as I set up the solution variables. I need to specify which of the mold subdomains will come into contact with the parison. In this case, there's just one to modify, and I want it to have contact enabled. Then I can begin defining the mold motion. I want the mold to approach the parison and then stop when it's in the correct position. So first I'll specify that a translation velocity is imposed on the mold, and then specify that the velocity has no components in the X direction and the Y direction, and has a nominal value of negative 350 millimeters per second in the Z direction. For the Z component, I want the time dependency to be a ramp function, so that it begins at a certain velocity and then over a specified time period transitions to another velocity. Up until a time of 0.2 seconds, I'll have the multiplier for the velocity I specified previously be set to 1, so that the mold translates at the full velocity. And then almost immediately thereafter, I'll have the multiplier ramp down to 0 so that the mold stops. And that completes the mold setup, so I'll return to the task menu by clicking the upper level menu item in the lower menus. This concludes part 1 of this video series. In part 2, I will define the parison and set up the calculation of the results.